so first of all, thank you, Abhay, for letting me give a talk today. It's really a pleasure to be giving a talk here, and I think you guys are doing a really fantastic job running this math club. So, firstly, let me just introduce myself. I am Rishabh Sharma. I am a second year undergraduate student studying at the Chennai Mathematical Institute. I am currently pursuing my BSc in maths and computer science. So today I wanted to talk to you guys about graph planarity and why it's sort of important, and I'll try to give you guys some motivation as to why you should think about planarity and why people like how people use planarity in today's world to solve different kinds of problems. And then we will move on to explore the connection between planar graphs and convex polyhedra, which you already know from high school. So convex polyhedra are just 3D shapes like tetrahedrons and cubes and cuboids, stuff like that. So we'll see that connection and how it sort of gives us a correspondence between Euler's formula for planar graphs and that for polyhedra. So if you don't know what Euler's formula is, don't worry, I'll explain everything once we get there. And then we will sort of try to explore the idea of dual graphs, and then we'll prove Euler's formula for planar graphs. Okay, and from this sort of machinery that we build, we will try to prove some theorems and look at some results using this idea of dual graphs. And then sort of, so this is our main agenda for today, to prove Euler's formula for planar graphs and use this to give a proof for the non-planarity of K5 and K33. So K5 and K33 are the names of two graphs, which I will explain what they are when we get there. And in the end, if you have time, we can try to look at a nice fun application of the idea of dual graphs, which is Sperner's lemma. So yeah.
Yeah, I wanted to ask about the prerequisites required for this lecture.
Prerequisites are you should be comfortable working with graphs. Like you should have a basic idea of what graphs are, what some basic kinds of graphs are, like trees and cycles, and some idea of connectedness and all that. Are you comfortable with that?
Yeah, sure.
Okay.
I have done some Olympiad problems on that.
Yeah, so that should be enough. Yeah. Okay, so give me 1 second. I'll share my screen. Okay, can you all see the screen?
Yes.
Okay. So let's start with some basic motivation for planarity. So I want you guys to think about this sort of a problem which electrical engineers face in the real world. So suppose you have a circuit that you want to design. Okay? Suppose you have a plan for a circuit, a blueprint for a circuit, and you want to make that circuit out on a circuit board. So maybe you all must have seen a circuit board, like if you have looked at some electrical components. So the idea of a circuit board is that you have this board, and on it there are some electrical components attached. And sorry, 1 second. So you have this circuit board with some electrical components on it, and you want to make electrical connections between them. and these connections have to be in such a way that they do not cross, because these connections are not insulated. So as you can see in this figure over on the top, these connections that you see, they run parallel to each other and they do not intersect, right? So uh, you want to make sure that they don't intersect because they're not insulated. And if they intersect, then the currents will just interfere with one another, and that's not something we want. So the idea is that you have um, a graph representing the circuit, the blueprint of the circuit that you have in mind, and you want to draw out this graph on a plane surface, okay, on this plane circuit board, in such a way that the edges do not intersect, except of course at the vertices. The edges intersect only at the vertices and nowhere else. So this is the basic problem that you want to tackle. You're given a graph and you want to find out if it's possible to draw it on the plane or not. Okay. And I mean, in circuit board design, even if you can't design a circuit which without any intersections, there are ways to sort of bypass these intersections with something technical that I do not know. But I mean, it's always feasible, more feasible to just design a circuit which is sort of drawable on the plane. Okay, so this is the basic idea. So now we'll sort of try to develop the theory of this. So we'll start with some basic definitions. So suppose you have a graph, and you can draw that graph out on the plane, right? In the manner I explained now, which was that the edges should not intersect. If you can draw out the graph in such a way, then the drawing itself is called the planar embedding of that graph. And the graph itself is called to be planar. So if the graph admits a planar embedding, then it is planar. That's the idea. And not every graph is planar, which you can see with an example. The example is again K5. K5 is, what is K5? K5 is you take 5 vertices and you make all possible edges between them. Right? So 5 vertices, how many possible edges are there? 5C2, which is 15. So just make all possible edges and you'll get the K5 here. Right? It's also called the complete graph on 5 vertices. Yeah, so you can sort of try to draw it out on the plane, and you'll see that no matter how you draw it, there will always be some sort of intersection there. So yeah, we'll try to prove this fact later in a more sort of rigorous way. But even if you just try to draw it, you can see intuitively why it doesn't work. Yeah, it's just and so an example of a planar graph is K4, which is you take again same logic, just take 4 vertices and make all possible edges between them. So this is K4 and this is the planar drawing of K4. So you can check that no edges intersect. Yeah. So one second.
Can you show the previous slide just for a second?
Yeah, sure. Oh, and I forgot to say, if you guys have any questions in between, just feel free to stop me and ask, or drop a question in the chat, whichever is more comfortable. Okay, let's move on. So one idea I want to introduce is stereographic projection, which will help us to make a connection between planar graphs and spherical polyhedra. So what is stereographic projection? It's just it's the name of a certain map, a continuous map. So suppose I take a sphere, right, and I remove this top point from it. Let me call this n. What does K33 mean? Don't worry about that now. I will explain what K33 means later. We'll use that later and I'll explain what it means. So, so you have this sphere and you remove one point from it. Okay. So I'll call that 10, a point 10, which you remove. So stereographic projection says that with this punctured sphere that you have, you can make a continuous map from this sphere to the real plane, to art. This is the real plane, the notation for the real plane. So I'll just denote by as the sphere minus n, sphere minus this part. So what we do is we take any point P on the sphere, we join n to P, and we extend this line until it intersects the real plane. Okay. So the setup is like you have this sphere, and below the sphere there is the real plane, and you take any point P on the sphere, join NP, extend it till it intersects the real plane. Let it intersect at a point Q, and so the map will just send P to this point Q. Okay? And we do this for all points. This is my map. I'll just call it phi for now. So this map sends P to this special point Q, special with respect to P. Yeah, and so you can see what this map does in a sort of intuitive way. You have this punctured sphere, so you have a hole in the sphere at the top. You expand this hole and just lay the sphere down on the plane. You're just expanding the hole till it, till the surface sort of starts resembling the real plane. Okay, so in that way, you're not making any cuts or tears in the sphere. You're just using that hole and expanding it to lay it out on this on the real surface, on the plane, right? And you can also see that this process of laying down the sphere is reversible. You can just take the plane and sort of wrap it onto the sphere with a puncture at the top. Right? Is the picture clear to everybody?
Yes.
Okay. So let's see some important properties of this map is that it is continuous, which we see because there are no. I mean, intuitively you can see because of that action of laying down, like opening and laying down the sphere. And if you can prove this rigorously, but I'm not going to go into that now. If you want to do that, it's your choice. You're welcome to do it. But intuitively, it should be clear why, with that picture, why is it continuous? And that picture also shows why it is invertible, because because of that, you can just wrap the plane onto the sphere. So it's continuous and invertible, and since it's invertible, it's also a bijection. So if you, I don't know if all of you know this, but if you have a function from a set x to a set y, and this function is bijective, invertible, then this function is also bijective. So this is a result you can check on your own. Yeah, so these are the properties that we will use and are important for stereographic. Is this clear?
Yes.
Yeah, so now we use this stereographic projection to make a connection between planar graphs and polyhedras. So actually, suppose I have a graph G. Okay? Suppose this is the planar drawing of the graph. Yeah. So I'm taking a planar graph and I'm drawing it on the plane. Now, I claim that I can use this planar drawing of the graph to get a spherical drawing of the graph. In the sense that if I can draw a graph on the plane, I can also draw it on the sphere without any intersection of edges. And for that, we use stereographic projection again. What we do is, so this is lying on a plane, right? This is lying on a plane. Then I just apply stereographic projection to this, wrap this plane onto a sphere. And since the function is continuous, I know that my graph will not, get torn apart, it will stay a graph, a continuous, continuous shape. And this will give me a drawing of this same graph on the sphere. It looks something like this. Yeah. And you can also see why this is uh, a proper drawing, in the sense that the edges don't intersect. Because if they did, if suppose this edge E1 and E2, and they have images E1 prime and E2 prime in there, suppose they intersect at, okay, wait, let me draw it in. Let me say that E1 goes to this edge E1 prime, and E2 goes to this edge E2 prime. Suppose they intersect at a point O, right? Then I know that the stereographic projection is invertible, right? So I can look at this E2 prime, and I can look at its pre-image, and I'll know that the pre-image of O will lie somewhere on this edge E2, right? Because it lies on the image of E2. So the pre-image of O, let me call it what, T, that lies on E2. Yeah. But O also lies on E1 prime, so its pre-image also lies on E1. But we know that E1 and E2 only intersect at this vertex, right? So we know that T actually coincides with this vertex. Yeah. So what this tells us is that if the images of two edges intersect somewhere, they must intersect at an image of a vertex. So in essence, the edges only intersect at vertices. That's what I want to say. Are there any doubts with this part? Okay. I'll take that as a no. And so what we did here was, we had a planar drawing of a graph. We used it to get a spherical drawing of the same graph. Right? And you can see that you can just invert this process. If you have a spherical drawing of graph, apply stereographic projection, and get a planar drawing of the graph in the same logic. So this is invertible. Then the next step is that I take a spherical polyhedra. So something like a tetrahedron or a cube or octahedron, something like that. Yeah. So suppose I take a tetrahedron. Yeah. And what I do is I sort of inflate this. So I have a 3D figure, I inflate it till it resembles a sphere. So what I will get is a sphere, but on the sphere there will be markings of, if you can preserve the markings of the vertices and edges, do that and you'll get something like this. Something that looks like, right? I hope everyone agrees.
Yes.
And yeah, so now again, I mean, you had a spherical polyhedra, you inflated it to get a drawing of some graph on the sphere, right? And of course, you can always reverse this. You can just deflate the thing and you'll get your polyhedra back. So we saw two processes and both of them were reversible. But I mean, you see this drawing is the same as what I did there. So once I get this drawing of a graph on a sphere, I can apply stereographic projection to get a drawing of the same graph on a plane. And what will that look like? It will look like this. I mean, this is K4, which I explained a little earlier. So we see that the tetrahedron is sort of related to K4 in the sense that I take the tetrahedron, expand it, I project it onto the plane, and I get a K4. Yeah. So, and once I get this graph, like starting from the polyhedra, once I get the graph, I can reverse this process. What does spherical polyhedra mean? Spherical polyhedra means that like the polyhedra we used to see in school. So like tetrahedrons, cubes, cuboids, icosahedrons, octahedrons. So stuff which doesn't have like holes in them, you know, like stuff which you can sort of deform and get into the shape of a sphere is what I mean. So if I have something like something looking like this, sorry, some 3D figure which looks like a ring. Yeah? This is also polyhedra, but this is not spherical. Why? Because I cannot deform it to make a sphere. However hard I try, the deformation will still contain the hole, right? There will still be a hole in that. So if there is a polyhedra which can be deformed into a sphere, I call those polyhedras spherical polyhedras. Does that make sense?
Yes.
Yeah. Okay. Thanks for the question. And okay, so we see sort of correspondence between these kinds of polyhedras and the planar graph. But this correspondence is sort of unidirectional in a way. Why? Because okay, yeah. Okay. So I think this correspondence is sort of unidirectional. Why? Because I cannot take any planar graph and associate it with a polyhedra. Because, for example, if I take the triangle, the graph which is just a triangle, and I do this sort of action with it, like I draw it on the sphere and then try to deform it into a polygon, you can see that that is not possible because the drawing on the sphere would be just sphere with a triangle on it. How will I deform it to make a polygon, polyhedra? So not all planar graphs have a polyhedra associated with them. Some of them do, and this sort of gives us an idea of why planar graphs can satisfy Euler's formula um, in some way, right? Because I mean, we know from school that Euler's formula is something. So, okay, what is Euler's formula? I must say that first. So, if I have a spherical polyhedra again, and I count its number of vertices, edges, and faces. So, again, let's take the tetrahedron. It has 4 vertices, 6 edges, 1, 2, 3, 4, 5, 6 edges, and 4 faces. Yeah, and I see that this thing satisfies this relation. So Euler said that this relation is special and it holds for all polyhedra of a specific type, which he called spherical polyhedra. Yeah. So this is a special relation for spherical polyhedra, which we have seen in school someday. But for now, we're going to assume that we do not know the proof of this. Okay? We are going to prove this using planar graphs. So what we're going to do, the plan is that we're going to we're going to prove this formula for planar graphs, yeah, and use that to deduce the Euler's formula for polyhedra using this correspondence that we just saw. Yeah. Because so, for example, if I can prove the Euler's formula for all planar graphs, I can I also prove it for the planar graphs which have a polyhedra associated to it. Yeah, and then from there, using this correspondence of drawing it out on the sphere and then deforming it to get a polyhedra, I'll know that okay, Euler's formula also holds for spherical polyhedra. Does that make sense? Everyone? Okay, cool. So let's go on. Mm, Now I want to introduce the idea of dual graphs, dual of a graph. So, so this idea is that suppose I have a graph which has a planar embedding. I draw its planar embedding out. So here let's take the same example. K4. And now we see that this drawing, this is on a plane. Okay? This is my plane, and this is the drawing. So this drawing, in some sense, divides the plane into various regions, right? So I have region number 1, 2, 3, 4. Divides it in 4 regions, and one of them is okay unbounded, but still a region. So I account for that. So the idea is to associate vertices to each of these faces, to each of these regions. Yeah, so I call these regions faces. So all of these are faces. I call this F1, F2, F3, and F4. Yeah. And to each face, I associated a vertex. So for each face, I associate a vertex. I just draw it inside. Then this is like a standard way to draw duals. So for each face, associate a vertex. And whenever you see that two faces are adjacent, like they share an edge, we draw the edge joining those two faces. So for example, face 1 and 2, they share this edge. So I draw the edge corresponding to this edge, joining F1 and F2. Similarly, F1 and F3, they share an edge, which is this one. So corresponding to this edge, I draw another edge which joins F1 and F2. Similarly, for F1 and F4, F2 and F4, which share this edge, F2 and F3, and F3 and F4. Yeah. So this is the construction. Once you are done with this drawing, this is called the dual of the graph. Dual of, say, K4 in this case. Okay. And so some terminology we will be using later is, okay, is everybody fine with the construction of the dual? Does anybody have a doubt?
Yes.
Okay. Okay. Uh, so some terminology you need to be aware of, which we'll use later, is the degree of a face. So, okay, so before that, the boundary of a face. So given any face, the boundary of the face is the collection of edges bounding that face. So for example, in face 3 here, this edge, okay, I should name edges. Okay, so for face number 3 over here, we see that let's change the one. So this face, sorry, this edge, and this edge are all bounding the face number 3. So I say that these edges form the boundary of face number 3, and similarly for face number 1, I get that these 3 edges on the outside are its boundary, right? And the number of edges in the boundary of a face is called the degree of the face. So degree of a face, F1, Fi, is the number of edges bounding that face. Yeah. And okay, we also say that an edge is incident on a face if it is part of the boundary of the face. So it's basically just another name for an edge bounding a face. It's the same thing. So okay, those are the sort of definitions and construction. So okay, so one thing you need to be aware of is that the dual graphs are dependent on the planar drawing of the graph, and not the graph itself. So you can have a graph which admits two different planar embeddings, and both of those embeddings give you two different dual graphs. That can happen. So dual graphs is not unique to a graph. A single graph can have multiple dual graphs. For example, if I draw this, yeah, and another drawing of the same graph would be this, then what is the dual graph of the thing on the left? Let me change color, and I have this face, the unbounded face, and two bounded faces. Now, okay, this edge is sort of a hanging edge, and this. So how do I draw the edge of the dual graph corresponding to this edge? Since it is part of only one face, I just draw a loop, like a looped edge, which just joins, this outer face to itself. So I call this F1. And F2. So for this edge, I just draw this edge which loops around itself and joins F1 to itself. Yeah. And then for F1 and F2, I have two different edges separating them. So for each edge, I draw one edge for the dual. Similarly for F1 and F3. Yeah, and now over here, I get F1, F2, F3. Now over here, the hanging edge is in F2. So I get a loop edge on F2, and then F1, F2, and F1, F2 again. Similarly, F1, F3, F1. So you can see that these two graphs are not actually the same. Okay? Because you have three vertices in both, but the layout of the edges is actually different. If you just stare at it for a minute, I think you'll see that. Yeah, because so I have three vertices on the left. I have a loop over here, double edge over this, double edge there, and three edges here, three vertices there, double edge, but the loop is on the second vertex now. Yeah. So these graphs are not okay. What is the degree of F1? Degree of F1 would be okay. So you look at the boundary of F1. What is the boundary of F1? You start from this vertex, so you go like this, one edge, two edge. So you sort of count this hanging edge twice. You start from this vertex, you go around the shape, and you come back there. So you count this edge twice. So you have at 1, 2, 3, 4, 5, 6. The degree of F1 is 6 over here. So yeah, that is a good point that has to be made. If you have a hanging edge, then that has to be counted twice in the degree and in the boundary. Okay. So let's move on. Okay, so another exercise would be to show that the dual of a graph always remains connected. In the sense that it doesn't matter if the original graph is connected or not, the resulting dual graph will always be connected. So I want you guys to try this for 1 minute and let me know if you have any ideas. Does anyone have any idea of how to do this? Okay, maybe I'll explain. Uh, so let's just take an example. Suppose I have this graph. Suppose it is disconnected. Then the faces are this, right? Connected. So what does it mean for a graph to be connected? It just means that given any pair of vertices, I can find a path from this vertex to the other vertex. Yeah, that's what it means for a graph to be connected. So in here, if I look at the dual graph, the vertices of the dual graph are just the faces of the original graph. So I'm basically asking if, given a pair of faces, can it go from one face to the other? That's the basic idea. And of course, like in this picture, you can obviously see that you can in fact go from a face to the other. Like I don't want to prove this rigorously, just sort of give you an intuition. So the intuition would be that you can think of the Earth, like the ocean would be the unbounded surface, the unbounded face F1 in this case, and the bounded faces would be the land masses, right? So from any given landmass, you can just travel anywhere you want because well, the world is connected. So that is fine, I think. Um, okay, let's try to move on. Mm. Ah, this is another exercise you guys can do. The dual of a graph G is isomorphic to G if and only if the graph G is correct. So what am I saying is, suppose you have a graph G, its dual is G dash, yeah, and you take the dual of the dual, so you get another graph which is G double dash. I'm saying that G is isomorphic, or let me not say isomorphic. Let me say that G and G double dash are the same graphs if and only if G is connected. So just try to do this and tell me if you get any ideas. So okay, so does somebody have an idea? Maybe first you can try to show that if the graph G was disconnected, then G and G dash, G double dash are not the same. G double dash is necessarily connected. Yes, that is true. Because uh, G is just any graph. I'm assuming that G is disconnected. Yeah. If I take the dual, uh, the dual G dash is necessarily connected because of exercise number 2. If G dash is connected, then G double dash is also connected because it's again a dual. So G double dash is connected and G is disconnected. So those can't be the same. Okay, does everybody get the idea? If anyone has any doubt, please feel free to ask. I'm as nervous as you are, maybe even more. Okay, so that is one direction. The other direction would be that if G is connected, then G and G double dash are the same. So that I think I should just explain the idea. Uh, uh, so suppose that G is connected, and just look at a single vertex. Just look at what is happening around a single vertex. So I have some edges incident on that vertex, and these edges, they, you know, harbor like the bound faces, like different faces. So let's say f1, f2, f3, f4, f5. I mean, it's possible that f1 and f2 are the same face because this edge might be a hanging edge. In that case, f1 and f2 are just, merged together. But that case, I think you can handle. I leave for you to handle it. So the basic idea, I'm just going to explain the basic idea, is that once you draw the dual of this graph, what you get is something like this. Yeah, something looking like this. In this region, in this local region, you get this. Yeah, and similar things happen around the vertices. This vertex, let's say V. So this vertex V is connected to, say, A, B, C, D, and E. So V gets surrounded by edges, right? These, okay, we should use a different color. So these are the edges of the dual graph, and they sort of surround V. Right? So they make a face in the dual graph which contains V. Yeah, and similar things happen around these other vertices. So there's something containing E, there's something containing B, C, and A. Everything. So you get this dual graph, and once you um, take the dual again. So what will you do in taking the dual again? You'll take the space of the dual, you'll assign a vertex to it. I'm saying let that vertex be V again. Just keep that vertex there. Similarly for every other face, you'll get those same vertices back. And then the edges will be again the same because each edge is corresponding to this sort of the dual drawing. I mean, I know this is a very hand-wavy argument, but I just want to give you the basic idea, and you can write it up on your own. Convince yourself that this works properly. Yeah, is the basic idea of what we can do is clear. How will we use the connectedness in the argument? Okay, good question. Um, so I think the connectedness is being assumed somewhere while making this phase. Like I'm assuming that C will be included in a phase, and B will be included in a phase. I mean, I don't know what is going on outside uh, this local region of focusing in on B. So um, okay. If that is something I'm not sure of at the moment. Um, but you can think about this. I think it's not, it shouldn't be too hard to account for the connectedness in the argument. Um, yeah, but I can't like hook up an argument right now. Um, it's okay. You can try to do this on your own. Try to see where connectedness fits in. And if you have doubts, if you want to discuss anything after the class, about this or anything in general, my email ID is given at the bottom. You can mail me and we will discuss. Okay, I don't know if you can see the bottom. I'll just write this email ID out. This is Rishabh@CMI. Okay. This is my email address. If anybody wants to, or maybe I'll just write it in the chat. Actually, anybody wants to connect with me later after the talk, feel free to mail. Okay, let's move on. So this is sort of an important result we will use later to prove Euler's formula. So the result says that suppose I take a graph, I take a planar embedding of it, yeah, and for every face, I take their degrees and I add all these degrees up. Then this sum will equal twice the number of edges of G. This is somewhat similar to what we have in, like the result we have, it says that if you sum up the degrees of all vertices, you get twice the number of edges in a graph. This holds for any graph G. For any graph G, if you just sum up all the degrees of all the vertices, you get twice the number of edges. And this result is saying that if I sum up the degrees of the faces, I get twice the number of edges. Any idea how to solve this using dual graphs? Anybody can answer. Even if you don't have a full idea, maybe just a hunch or anything, feel free to share. You can associate an edge separating two boundaries. Okay. So you're saying we associate that to both the faces, like that edge contributes 1 to both the degrees of both the faces. Yeah, that's the idea. So you have this drawing of the graph. Let's draw something. Okay. Then any edge I take, it separates. It has two faces on either side of it. Like in this particular example, this is F1 and F2. I take this edge. I take this edge. This has F1 on one side, F1 on the other side. Similarly, this has F1, F1 on both sides. This edge has F1 on this side, F2 on this side. So any edge I take, it has two faces on either side of it, and so it contributes 1 to the degree of both those faces. So for example, this edge contributes 1 to the degree of F1, and then again 1 to the degree of F1, because we saw that the hanging edge contributes 2. So this is another way to account for that. that any edge has faces on both the sides, so it contributes 1 to both the degrees. Yeah. So if I just so this is true for any edge, right? So I can just take twice the number of edges, and this will be the sum of all degrees, because I mean each edge occurs twice in any each edge has each edge contributes to 2 degrees. I'm sorry. Let me rephrase this. Any edge has a face on both the sides, and it contributes 1 to both those degrees. Yeah. So if I just sum all the degrees, any edge contributes 2 to that sum. Yeah. So twice the number of edges equals the sum. Is that clear to you?
Yes.
Okay. Cool. Um, let's try to prove Euler's formula using everything we have done till now. So the basic idea we'll use is that of induction. So and induction on the number of edges. so okay. In Euler's formula, we are assuming that G is a connected graph, right? G is a connected graph which has a planar embedding. Yeah. Then we say that this relation, in which V is the vertices, E is the number of edges, F is the number of faces, these quantities satisfy this relation. That's what Euler's formula is saying, and this is very closely related to the same formula for spherical polyhedra that we saw. So since we assume that the graph G is connected, the idea is to use induction on the number of edges. So the base case would be to take the case E is equal to 1. In that case, the graph will be a simple edge, right? Just one edge with 2 vertices, V1, V2. Because the graph is connected, I cannot have more vertices without making the graph disconnected. Yeah. So this is the case in E equal to 1. And here you can see that there's only a single face, the single unbounded face. Yeah? So F is equal to 1, E is equal to 1, V is equal to 2. So in this case, you can see that 2 minus 1 plus 1 is 2. So the induction hypothesis, the base case holds. Now, suppose that Euler's formula holds for E equal to K. If I have a graph with K edges, let me say K minus 1. If I have a graph with K minus 1 edges, I know the formula holds. I assume the formula holds. Then I try to prove this for equal to K. Okay. So how will I get a graph with K edges? I can take a graph with K minus 1 edges. So suppose I have this, I have this graph, and to build the graph with K edges, I just add an edge somewhere in this graph. Okay. So suppose that adding this edge makes the graph that I want. Then what did adding this edge do? It did not change the number of vertices. I did not introduce any new vertex. Okay. So the vertices remain the same. The number of edges increased to K, and the number of faces also increased by 1. Yeah. So okay, let me this was my original graph. It had V vertices, F faces, and K minus 1 faces. And over there I have V vertices, K edges, and F faces, F plus 1 faces, because one of the faces had been divided by this new edge. The new edge was this. So the introduction of the new edge divided one of the faces, and hence the faces got increased in number. So now if you apply the formula, you see that b minus k minus 1 plus f is equal to 2, right? This is what the formula says. And in this case, we get that b minus k plus f plus 1 equal to 2. But you just see that these are, I'm sorry. I need to show that this is equal to 2. But we see that these are in fact the same expressions, because this is also v plus f minus k plus 1 is the same as this, and hence this is also 2. So in this case, Euler's formula holds. Now, another possibility of adding an edge would be to, hanging edge. Yes, and thank you. So I have this original drawing, and I introduce an hanging edge. So suppose, sorry, new color. So this is my new introduced hanging edge. So in this case, what happens is the number of faces does not increase. Okay, I had f faces before, I have f faces now, because the hanging edge does not cut a vertex into 2. Sorry, cut a face into 2. The number of faces remain intact. The edges increase by 1, so I have k edges. And the vertices also increase by 1 because I introduced another vertex for the hanging edge. So I have v plus 1 over there. Again, apply. Let's look at that that expression, which is v minus e plus f, and we see that this is again the same as this expression, so which is equal to 2. So again, this is equal to 2, and this finishes the inductive part. So by mathematical induction, you can conclude that Euler's formula holds for all planar graphs. Okay. Is that are there any doubts?
No.
Okay. Anybody else? Any doubts? Okay. Okay. So we finished proving Euler's formula for planar graphs. And now again, we can go back to that stereographic projection thing and use this to, get Euler's formula for spherical polyhedra. But this I'm leaving to you guys because I've already explained the basic idea behind it, the stereographic projection thing, and just try to think about it, how it connects to, if the polyhedra connect to the planar graphs, and how the Euler's formula just translates, this translates into that for the spherical polyhedra. So now we will try to look at some corollaries of Euler's formula, and these corollaries will be important in proving why K5 and K33 are non-planar. Again, K33 I haven't explained what it is, so let me just do that now. So K33 is the complete bipartite graph on 3 and 3 vertices, which means that I take 3 vertices here and 3 vertices there in 2 different packets, suppose, and I just join every vertex on the left to every vertex on the right. So for every vertex on the left, I get 3 edges, and the graph will look something like this. Just check that I have drawn all the possible edges, and this is what K33 is. Okay, somebody was asking what K33 was, and yeah, this is what it is. Okay, so now we will try to prove this corollary. Okay, sorry. Yeah, let's see. Now I'm assuming that G is a simple planar graph. What is a simple graph? Simple graph is just something which has no loops or multiple edges. So what are loops and multiple edges? Loop is something like this. You take a vertex and connect it with itself. That's a loop. And a multiple edges would be, you have an edge between two vertices, and you have another edge between the same pair of vertices. These are multiple edges. Okay, so a simple graph does not have a loop or a multiple edge. Degree greater than 1. Sorry, what do you mean? Do you have a question? For multigraphs, degree is greater than 1. Okay. But we are not dealing with multigraphs over there. We are dealing with simple graphs for now. For this particular result, we are saying that the graph cannot have these loops and multiple edges between vertices. Okay, so the graph will look something very simple, like a triangle or something like this. It cannot have this loop or this multiple edge, something like that. These are not allowed. Yeah. Okay. So I'm not sure if you had a question with that or was it just comment. If you have a question, you can try to write it in the chat again if I'm not understanding it properly. Or maybe just say it out. Okay, it's clear. So yeah, so we move on with this. So the idea here is that any face in this planar graph will be bounded by at least 3 edges. Why? Because suppose you had a face which was just bounded by a single edge, then the face would look like this, right? It will be a loop. But loops are not allowed, so the faces can't be like this. Similarly, if the face was bounded by 2 edges, then it would look something like this. This is again not allowed because these are multiple edges. So the only possibility is that degrees of all faces are at least 3 for all faces in the stuff. Yeah. So this holds. That's why that's where we're using that the graph is simple. Okay, so once we do this, now we know that we did that exercise which said that the sum of degrees of all faces was twice the number of edges. But now we know that the degree of every face is greater than or equal to 3. So the sum of the degrees is at least 3 times the number of faces. Yeah, this is the number of faces now. Okay, wait. Let me use some different notation. It's quite good. Okay, so this means the number of faces. Number of faces. Yeah. So this holds because of this condition. And since we know that the sum is equal to 2e, I can just replace this. 2 is greater than or equal to 3 times the number of faces. And now what we can do is, sorry, I'm just making some space over there. Now you can use Euler's formula again, which is v minus e plus f is equal to 2. So we use that, we get that v minus e plus f. Now we see that this f is actually at most 2e by 3, right? I mean, this inequality gives us this. The number of faces is at most 2e by 3. So we get that v minus e plus f is at most v minus e plus 2e by 3. Yeah, but this is also equal to 2. So you get this relation. Yeah, and So this gives us that 2 is at most v minus e by 3, which means that 6 is at most 3v minus e. I'm just multiplying by 3 on both sides. And this is the same as the inequality we wanted. Okay. Are there any doubts? Also, if you can't understand my handwriting, let me know. I think it should be correctable. Okay. I hope it's clear. If there are any doubts, just let me know. So now we are going to use, actually, let me see. Okay, I'm a little short on time, so I'm going to skip this probably. This is not very important for us right now. But if you want, you can try this on your own. If you get time, just take a screenshot or write it down with you if you are interested, and try it out on your own on your free time. This is a very simple exercise using the previous corollary. Okay, so we'll move on to our next sort of main theorem for today, which is that K5 is non-planar. So K5, let me recall, was the graph which had, 5 vertices, and all possible edges were made in this graph. Yeah. So this was K5. Now I'm saying that K5 is non-planar, and you can show this using the corollary that we just did, right? Using the result that E is less than or equal to 3v minus 6 for a planar graph. Okay. So this is actually very simple. What we do is we assume that K5 is planar. So we suppose that K5 is planar. If it is planar, then we also know that it is simple, right? Because it has no loops or multiple edges or anything. It's a simple planar graph. So we can apply the previous corollary, which means that this result, that E less than or equal to 3v minus 6, must be true for K5. Yeah. But how many edges does K5 has? Does K5 have 5 C2, right? This is 15. 15 edges it has, because for every pair of vertices you make an edge. So there are 5 C2 or 15 pair of vertices. So you make 15 edges. And the vertices are just 5. So the right hand side is in fact 3 into 5 minus 6, which is 9. So that our corollary says that 15 is less than or equal to 9, but we know that's not true, right? So K5 cannot be planar by contradiction. So K5 is in fact not. Yeah, is that clear? Are there any doubts? Okay, so let's see another sort of a useful lemma, which we'll use to prove the non-planarity of K33. So this lemma, okay. So now we assume that G is a planar, simple planar graph, and this time it is without a 3 cycle. So a 3 cycle is just a triangle. Yeah. So we are assuming that our graph does not contain a triangle in it. So for example, it could look something like this, or maybe even add a few more. Yeah. But it can't be like this, because then it will contain this triangle. So we assume that G does not have a 3 cycle or a triangle in it. Then we show that this is true. And again, the idea is very, very similar to what we did for the previous result, the E less than or equal to 3 minus 6 result. So we're going to use the exact same idea. So what we do is, again, we look at a face. Okay, so we look at a face of this graph. Yeah, suppose it's this one. Now we know that the degree of f1 cannot be 1 or 2 because the graph is simple. But we also know that it cannot be 3 because if it were 3, if the degree of a graph were 3, of a face were 3, then it would be bounded by a triangle, but that's not allowed. They're not allowing that. Uh, so yeah, degree of a face cannot equal 1 or 2 or 3. So the degree of every face has to be at least 4. That is the crux of this. That's the main idea. So again, you use that summation, so degree of faces summation. This is equal to 2 times e. And you know that each of the degree is at least 4. So this sum is at least 4 times f. And e is at least, sorry, e by 2 is at least this event. Again, same thing. We use Euler's formula. We know that v minus e plus f is less than equal to v minus e plus e by 2. Using this inequality, this is equal to v minus e by 2, and this side is 2. So we get that 2 is at least v minus e by 2. And this gives us that actually 4 is less than equal to v minus, sorry, 2v minus e. And you can see that this is the same as what we wanted. Okay. Okay. Are there any doubts in this? Okay. I hope not. And so yeah, now let's try to use this to prove that K33 is non-planar. The idea is very, very similar to the previous proof of K5 is non-planar. So can somebody tell me what to do? Okay, so the idea is to use the previous lemma, right? But to use the previous lemma, you need to make sure that K33 has no 3 cycle. Has no 3 cycle. How can we make sure of this? Why does K33 have no 3 cycle? Can somebody explain? Again, K33 was this graph. Draw it out. You have 3 vertices on both sides, and you connect everything on the left to everything on the right. Okay, this is K33. So can somebody tell me why K33 has no 3 cycle?
Because if we move in any 3 edges, it will not return to the same point, to the
Yes.
same vertex.
Yes, exactly. So suppose I want to find a 3 cycle in K33. I start on the left. So I start at this vertex. Okay. And to make a cycle, I have to go to the opposite set of vertices, right? Suppose I go here, and then I have to come back, yeah, because there are no edges inside these sets. The edges are always across the sets, so you have to come back. But then these 2 vertices cannot be connected because they are in the same set and they don't have edges between them. So you cannot find a triangle or a 3 cycle in this K33. And for similar reasons, you can just extend this argument, generalize this argument to say that you cannot find any odd cycle in K33. can't find odd cycle in K3. Actually, even you can generalize this. You can say that you can't find an odd cycle in any bipartite graph. So if you don't know what these words mean, don't worry, we're not going to use this. This is just for people who know and uh, might be interested. So if you, so yeah, this is just for your knowledge uh, that you can't find an odd circle in any bipartite graphs. So does anybody have a question? Okay. So how do we use our previous lemma for this? Again, we know that suppose that K33 is planar. Let K33 be planar. Then we know that K33 has no 3 cycle, and hence it satisfies the conditions for the previous lemma. And so you can say that the number of edges in K33 is at most 2v minus 4. Now, what is the number of edges in K33? It's just 9, okay? Because everything on the right is connected to everything on the left. So 3 times 3, that is 9. And the number of vertices is 6. So this means that 9 has to be less than or equal to 12 minus 4, which is 8. Again, this is absurd. So K33 has to be planar, and this assumption was wrong. So K33 is planar. Sorry, K33 is non-planar. Sorry for that. Yeah. So we assume K33 is planar. Did I have a contradiction? That means K33 is non-planar. Okay. Does anybody have any doubts in this?
No.
Okay. Now I'm almost done. I have like 10 minutes left. So I'll explain what Sperner's lemma is and how to use dual graphs to prove Sperner's lemma. It's actually a very interesting little fact. So let me explain what the lemma says. It says that suppose I have a triangle. Okay. And I color the vertices. Okay. Before that, I have this triangle and I subdivide this triangle into smaller triangles. So I draw some, edges and vertices inside this triangle. Yeah. So that the triangle is divided into smaller triangles. Yeah. So every piece, every area here is a triangle. That is the condition. Okay. And now also like these triangles should, if you take a vertex of a triangle, it should not lie on the interior of an edge of another triangle. So you shouldn't have something like something like this, because then this triangle has its vertex lying on the interior of this other triangle, and that is something that is not allowed for now. So we are sort of dividing the triangle into little triangles in some nice way, and now we need to color the vertices of this triangle. Okay. So the way to color it is that I choose 3 different colors. So suppose I choose red and green and blue. Then I take the 3 vertices of the bigger triangle, the original triangle, and I color them in different colors. So suppose this one is red, this is green, and this is blue. Okay. and I can color the interior vertices, so these vertices, in any way I want. Okay, so I can just color them blue or green. Yeah. And for the vertices on the boundary, that is on the edges of this triangle, I say that if I have a vertex lying on this, green red edge, then I color it with either green or red. I do not use blue there. So for any vertex on this edge, I only use green and red colors. Okay. So for example, this is red, this is green. Similarly, for the other edges, here I will use only blue and red. Suppose I use only red. Similarly for this. So this is how I'm coloring my setup. Yeah. So Sperner's lemma claims that once I have this setup, I can always find a small triangle, in this subdivision, such that the vertices of the triangle are differently colored. Okay, let me just write it. Can always find a good, let me just call it a good triangle. So a good triangle is something which has, distinctly colored vertices. So for example, in this setup, the triangle will be this. So now let's try to prove this. Okay, hello, Abhay, are you there? I'm thinking, okay, I will continue. No, I can't hear you properly. Actually, I can't hear you at all. And I was just asking if I can continue for like 10 extra minutes. Okay, sure, thank you. Yeah. So let's try to prove Sperner's lemma now. So the idea is to use dual graphs, to use them in a sort of a clever way, such that you can sort of tie this good triangle condition to something more feasible, to something more related to graphs. So okay, so you see that this is a planar graph, right? This in itself is a planar graph. Yeah, and I can take its dual as it is, but I will do it in such a way that this finding a good triangle condition becomes more accessible. Okay, what do I mean? Let me first explain the construction of the dual graph. So what I do is for every face in this graph, I associate a vertex again, as we normally do. Yeah. And instead of connecting an edge for corresponding to every edge, I only make edges corresponding to edges which are, say, red, green in color. Okay. I just choose two colors, red and green. And I'm saying that whenever I make an edge of the dual graph, it has to be corresponding to some edge which is red, green in color. Okay. So for example, now if I try to draw the dual graph of this, I have this red, green edge over here. Yeah. So the corresponding edge of this in the dual graph would be connecting this to the outer face. Yeah. Similarly, this red, green edge gives me a corresponding edge. Similarly over here. Similarly over here. And I think that's it. Yeah. So these are the only red, green edges, and for each of them I associate an edge in the dual graph. And I don't make any more edges. And I just want to use this. Yeah. So the thing that is special about this construction is that if I have a a triangle which is good, as in, it has all the three different colors in it. So red, green, and blue. Then the vertex associated to it has degree 1, right? Because it has only one edge uh, corresponding. It has only one red-green edge incident on it. So the degree of this vertex is equal to 1. Yeah. And suppose I have a triangle which is not good. So suppose the triangle is, only uses two colors. Then what will happen is, if it uses red-green colors, then it can be that this vertex is red, this is red, this is green. In which case, this vertex has degree 2 because of these two red-green edges. Another case would be it being red, green, green, in which case, again, the degree would be 2. Yeah. And if the triangle does not use red and green, it uses some red, blue, or green, blue, then there will be no edge corresponding to a red, green coloring, right? So the degree will be 0. Yeah. Similarly, if the triangle is just monochromatic, then also I cannot find a red, green edge. Then also the degree will be 0. So I sort of partitioned the cases for a triangle coloring nicely into conditioning for the degrees. So I know that if the degree of a vertex in the dual is equal to 1, this is equivalent to saying that the corresponding face is a good triangle. Face is good. Yeah. And if I have an even degree, if I have a degree of 2 or a 0, then that's not a good triangle. So in this way, I sort of tie the condition of a good triangle into something more accessible for graphs, their degrees. Yeah. So now the idea is to show that the interior of this this graph, as in the interior faces, there is one face which has an odd degree. The idea is to show that. Okay. But now we also have a vertex which is somewhat special, in the sense that it lies outside the triangle. Yeah. And it's special because, okay, let me say this. If you look at this edge, if you look at the edge opposite to the blue one, then I'm saying that it has an odd number of red-green edges on it. I'm saying it has odd number of red-green edges. Why? Because so you're starting on a line. Okay, you have to go from point A to point B. Point A is what, green in color, and point B is red in color. Sorry, point B is red in color. Point A is green in color, and you're traversing from A to B. Okay, and on the way there are other vertices which are either green or red colored. So suppose this looks something like this. Then I traverse from the left. I traverse from the left. And whenever, okay, so currently I'm at a vertex which is green. So whenever I meet a red vertex, I just say that, oh, I found an edge which is, red, green in color, because I changed my color from green to red. So I must have found an edge which is green, red in color. Yeah. So whenever I change my color, I say that, okay, I found a red, green edge. So for example, I start from here. I go to the next vertex. It's green, so I don't say anything. And once I reach the next vertex, which is red, I say that, okay, there must be a red, green edge before me. Yeah. And then on the next vertex, it's green again. So again, the color changed. It's again a red, green edge, and similarly here. So you're going from a green color to a red color while changing colors. And you can see that you have to change colors an odd number of times, right? Because if you change an even number of times, you will just get back to green. You start at green, if you change it an even number of times, you just get back to green. So you have to change color an odd number of times, and each color change corresponds to one red green edge. So since you start at green and end at red, you must have an odd number of red green edges between them. Yeah? Which is to say that this face must have an odd degree in my special div graph over here. Okay, and once I know that this external vertex has an odd degree, I recall something which I used in the middle of the talk, which was that the sum of all degrees of a graph, degrees of vertices of a graph, is equal to twice the number of edges, right? So the sum of all degrees of the graph is an even number, and I'm saying that one of the degrees is odd. This must mean that there is another vertex which has an odd degree, right? Because if there's only one vertex with odd degree, the sum becomes odd, right? But I know that the sum is even. Right? So there is another vertex with an odd degree, and since the vertex is not outside the triangle, it must be inside the triangle. So I have found an odd degree vertex inside the triangle. And since I found an odd degree vertex, it must be a good triangle because it corresponds, like it's an equivalent condition. Finding an odd degree vertex means I found a vertex with degree 1, which means that the face is in fact a good triangle. So that is Sperner's lemma. Does anyone have anything to ask? Any doubts in this proof?
No.
Sorry, it's the
Said it's clear.
okay, cool. Yes, so that's it from my side. If you guys have any questions you want to discuss later, you can always contact me.
Can you show me the slide of Sperner's lemma?
Yes, one second. There it is. Okay, so if you guys have any questions you want to discuss after the talk, I am writing my email again in the chat. You can use it to send an email to me, and I'm open to any sort of discussions with you guys. Yeah. So yeah, that's it from my side. Thank you guys for coming. And Abhay, if you have anything to say. Okay, I can't hear you if you're saying it. Okay, you can end the recording. Yeah.